This is a very short video just devoted to the topic of coordinate vectors and explaining what that means. So let's recall that if you have a basis for a vector space, then any vector can be written as a linear combination of vectors from that basis. If my basis has vectors, say, v1 through vn in it, then that linear combination looks like a scalar times the first vector plus a scalar times the second vector, and so on and so forth. And some of these scalars may, of course, be 0. Well, when you have an expression like this for x in terms of v1 through vn, the coefficients of that expression, those c1s and c2s and c3s and cn, those are called the coordinates of x. And because it's so special to this basis b, it's relative to the basis b. The coordinates are meaningless without having that basis as well. That's what we mean by a coordinate vector. And there's special notation which is often used for this with brackets. So x with a subscriptive b means that coordinate vector of x relative to b. And so it itself is a vector where you just take off the coefficients. c1, c2, all the way down to cn, is the coordinate vector relative to the basis b. Let us now look at two different examples. We're going to write down the coordinate vector relative to the standard basis and then relative to some other basis. Writing the coordinate vector relative to the standard basis is the easiest kind of example. So let's suppose we have some other basis. Let's take 1, 0 and 1, 2. That'll be our basis for our 2. It's a non-standard basis. And what if we're given that the coordinate vector relative to this non-standard basis is 3, 2? We want to write down the usual coordinates of the vector x, not the coordinates relative to this non-standard basis. Well, what you would do is you write out your vector x as that linear combination. This notation means that when you write out that vector, you have scalar 3 times the first basis vector, which is 1, 0, plus scalar 2 from the coordinates times the second basis vector. So we take the second vector from the basis. And now if we simplify this expression, we could see that that's 3, 0 plus 2, 4, which adds up to be the vector 5, 4. And the way we normally write vectors is in terms of the standard basis. So that's 5 times 1, 0 plus 4 times 0, 1, where I'm using my standard unit basis vectors for our 2 here. So the standard coordinate vector would be 5, 4. That's what we usually mean when we write down vectors, is it's in terms of the standard basis. And this is how you convert from non-standard to standard. In other words, 5, 4, which is the customary way to write a vector, is the coordinate vector for the standard unit basis. So we would denote that something like x, std for standard, or xi, something like that. Let's do one more quick example while we're on this topic. So in the second example, instead of starting with something that's given in terms of a non-standard basis and then converting it to standard, let's see what we would do if we're given a vector in the usual notation, but we want to write it relative to a non-standard basis instead. So let's say we're starting with a vector x, which is written in terms of the standard basis, the way we normally would, as 1, 2, minus 1. But now we want to write it relative to a different non-standard basis for R3, the basis b that we see here with these 3 vectors. Well, how would we go about doing this? You're going to be pleased to see that this is the same kind of problem we always solve. Let's think about what we're trying to solve with a formula. We want to be able to find scalars, c1, c2, and c3, so that if we write a scalar times the first basis vector out of that basis, plus a scalar times the second basis vector, plus a scalar times the third basis vector, it gives us the expression 1, 2, minus 1. So in other words, we're just trying to determine these scalars, c1, c2, and c3. But wait, this is the same problem we're always solving. This is just solving a system of equations. Instead of x, y, and z, now we're looking for c1, c2, and c3. So just like we solve all the other problems, we're just going to use Gaussian elimination to solve this. Let me just repackage this problem, and then you'll see what I mean. To solve this problem, what we're going to do is just take the matrix 1, 0, 1, that's this vector first, 0, 1, minus 1, 2, that's this vector second, and then the third vector third, packaged up into a matrix. And now we're just looking at the matrix equation A, x equals b, solving as we always do for x. The coordinates of x are c1, c2, and c3. And these are the coordinates of the vector relative to the basis b that we're after. And if you would like to see the solution, there is a unique solution for this particular matrix, which happens to be invertible. I'm not going to work through the row reduction algorithm on this one. I'm just going to give you the answer. And if you need a little extra practice, I encourage you to work through it and make sure that you get this solution too. But the solution that I found solving this was C1 equals to 5, C2 equals minus 8, and C3 equals minus 2, just by doing the regular Gaussian elimination procedure for solving a system. So in terms of the problem we're looking at here, we want to know what the coordinate vector of x was relative to this new basis. Well, the coordinate vector are those three numbers, 5, minus 8, and minus 2, written down in a vector and given now this special notation x sub b.